This is the solutions for Physics 110, Master Set, Chapter 2, Version 5. So we have two metal balls that are the same size, but ball A is 4 times the mass of ball B. The balls are dropped from the roof of a single-story building on Earth at the same instant, or dropped at the same instant, and fall towards level ground. When each hits the ground, it is stopped at a distance of 1 millimeter. Neither ball bounces. Ignore the effects of air. A key element of this is ignoring the effects of air. So we're not dealing with air resistance. So as long as air resistance is not a huge impact, you can actually try this at home. And as long as it's dropped over a short distance, such as you're standing and you drop two objects, and the object is not too light, like a feather would not work particularly well here, we can ignore the effects of air. So which hits the ground first? Well, objects should be falling, if we can ignore the effects of air, in other words, air resistance, with an acceleration of 9.8 approximately meters per second squared. In other words, the velocity will increase. The change in velocity will be 9.8 meters per second. So every second that passes by, it's going to increase that speed. And when I'm commenting on this, this has no regard to the mass. In other words, all objects should be changing their speed or velocity, depending upon how you want to frame it, at the exact same rate. So they both hit the ground at the same time. Now, since they are both going the exact same speed when they hit the Earth, then the question is, how much effort does it take to stop it? And at this point, the mass comes into play. Imagine that you have a fly coming at you at 1 meter per second, and you have an elephant coming at you at 1 meter per second. If you're going to both stop them both in the exact same amount of distance, the elephant's going to be a lot harder to do. So the heavier one, ball A, will have a greater magnitude of average force to stop it. And one of the reasons why I went to magnitude here is that otherwise we're dealing with a positive or negative. And that just is unnecessarily complicated right now. The main force which stops the ball, forces we have at this point in the course, we have our F-town, friction. Not really friction stopping it because it's not really rubbing against the earth. It's hitting the earth and going splat. Tension, there's no rope or chain or anything like that pulling on it. Other, I didn't introduce some mysterious force into the problem. Weight is not stopping it. That's what's causing it to fall. Normal force, the one that requires contact. It's the normal force which is actually stopping the ball. Problem 4. A boy throws a steel ball straight up, considering the motion of the ball only after it has left the boy's hand, but before it touches the ground, and assume that the forces exerted by the air are negligible. What's the main force? Well, once it's in the air, again, we have our checklist here. So forces exerted by the air are negligible. In other words, we can ignore it. So air resistance out. There's no friction, because this is after it's left the hand and before it's touched the ground. There's no rope or chain, so tension is out. Other, I didn't introduce anything mysterious in the problem after it's left the hand. Normal force is not in contact with anything, and what we're left with is weight. It is the force of weight. So as the ball is going up, we have weight acting down. As the ball is going up, the weight is causing it to slow down, and as it's coming down, the weight causes it to speed up. Now, sometimes students will write down gravity as the answer, and gravity, I contend, is not a force, even though it is often used as such. But the reason why I object to gravity being used here is that there are weight, the generalized force due to gravity, that's a subscript G, the gravitational constant, and acceleration due to gravity. These are all aspects of gravity. And these are all things that some students will just call gravity. They will use gravity to describe any of these, and they are not all interchangeable. So using gravity is too generic a term. It's a huge term, and what we need is just a small little part of it. So force due to gravity or gravitational force or weight are all acceptable answers here. Question 5. Sketch the sum of the vector. So so get close here. It's a sketch. That's the key word there, that you can eyeball it. So it doesn't matter the order in which I add these. I just take one of them, and why don't I just take that one? I take a starting point, and I'm going to try to draw it. Now, those are supposed to be pointing in the same direction and the same length. I now have a new starting point. I'm just going to pick this one. I'm just going to work my way around clockwise here. Might have gone a little bit overboard on that one. Yeah, it looks like it should have stopped right there. So I have a new starting point for the next vector. And then the last vector, I'm here, and now this is not the answer to the problem. This is just part. This is the addition part, but now to get the answer, an answer is a vector from where we started to where we ended. That right there is the resultant. Resultant has a head to it right here, and so don't forget to put that on, as well as it's from where you start to where you end. That is the sum of those vectors. Problem 6. Elevator is being lifted up an elevator shaft at a constant speed by a steel cable. We're ignoring all frictional effects. The elevator is rising. The force on the elevator are such that... All right, so we have a couple things here. It's up, we have a direction, and we have the fact that the speed is not changing. Since speed and direction are both not changing, that means that the velocity is not changing. So the change in velocity is 0, which means equilibrium. And if equilibrium is in effect, not only is, therefore, if the change in velocity is 0, that means the acceleration is also 0, and it also means that the total force, and this is just a symbol meaning sum, the total force is equal to 0. So therefore the forces up must equal the forces down. Well, right off the bat on A, we have the upward force of the cable is greater than the downward force. That can't be right. Upward force of the cable is equal to the downward force of gravity, because as this thing is being pulled up, we have this tension pulling up here, and we have its weight acting down. We're ignoring friction. We have tension. There's no normal force. It's not touching anything other than the cable, and that's what we're calling tension there. So those are the two forces. Upward force of the cable is smaller than, well, that can't be it because the total force has to be 0. Upward force of the cable is greater than the sum of the downward force of gravity and the downward force due to air. There is no downward force due to air. There is a slight upward force, and it's incredibly tiny, so that we can ignore it for the final answer. So if anything, there's an upward force of air. And the elevator goes up because the cable is shortening, and that's not really a reason because we're dealing with forces here, and the cable being pulled elsewhere is causing the tension, which is causing the pull up on it. So the answer is B. What directly exerts the force, and what is this force called, which accelerates us forward when we walk? So as we walk, and we'll just do absolutely spectacular sketch here, that when you walk, you are pushing your foot backwards. Even though you are going in this direction, and friction opposes motion, friction is actually opposing the motion of the foot. So you push your foot backwards. So you push on the ground in that direction. So if we did a force diagram here, the force on the ground is backwards, and therefore the force on the foot, the reaction force on the foot, must be forwards. Now, what force is that? Well, we have one object, the foot, in the ground, and the foot is rubbing against the ground. So therefore, it is friction. Now, you could make an argument for normal force here, but not always the case. That if we zoomed in on the space right here, if the ground is soft enough, and there's the foot, the ground is soft enough, we do have a normal force involved here. However, if it's flat ground, and I probably should state that, but if it's flat ground, then the ground does not indent like that, and the normal force is upwards. So that would be the direction of the normal force. And then down. Now, if you don't think friction is really the force there, then next time you get a chance to walk on ice, I recommend that you do so, and you'll find that it's a lot harder to walk because the friction has been reduced. Number 8 here. So this is year and second are units of time. That's not going to be the case. That should have been down here. Newton is a unit of force. Meters per second cubed, this is jerk. This is acceleration. This is velocity or speed. This is distance, position, or displacement. Pounds is a unit of force. Oh, so that actually would be 9. Kilogram meters per second squared, that actually is a Newton by definition. So 10 is also a unit of force. Typically, when we end up with kilogram meters per second squared, we just write newtons. And that, if you think about it, that comes from the formula of Newton's second law, F equals ma, that the units of force equal the units of mass times the units of acceleration. And so that would be a kilogram times a meter per second squared, which is a Newton by definition. Kilogram meters per second, this is a unit for momentum. Kilogram, that is mass. Joule, this is for joule, that's for work and energy. Inches per year, this is also a speed, any type of, or velocity, speed or velocity. Foot-pounds, this is work or energy. Foot is distance, displacement, or position. And then this is a made-up unit that I talk about when I get to momentum, just because I don't feel like writing out kilogram meters per second, that I create my own unit, and I'll talk about that when we get there. Now inertia, notice we didn't have inertia anywhere on here because inertia is a concept. It's actually not a quantity, and that's sort of misleading there, but you know, that's the way the game is being played. So actually that would be none of the above. So I apologize for that mistake earlier. Then down here again, force is a vector quantity. Direction does matter. Mass does not matter for direction. Doesn't matter where you are or which way it's going. Mass is still the same, so that is a scalar. It is a quantity, but inertia is not a quantity, so that would be neither. A 16 kilogram box has 2 forces acting on it. There is 24 Newton force acting east and an 18 Newton force acting north. And so I'm just going to draw a picture here and just establish, even though I think it's generally understood, you should establish conventions. And so we have 24 newtons acting east. So I have 24 newtons acting this way and 18 newtons acting this way. And so the question of the magnitude, well, these forces are right there and I need to add them together. I've got 24 newtons going to the right and I have 18 newtons going up. And so my total force is the sum of those two. And since that is a right triangle, I do a little Pythagorean theorem and I get 30 newtons. That's 18 squared plus 24 squared is equal to 900. And the square root of 900 is 30. The maximum of the force, if the forces shift, I get maximum when they're going in the same direction. If everybody pushes in the same direction, things move a lot more easily. So the maximum is going to occur if the 24 and the 18 are in the same direction. So that, you just add them together, 42 newtons is the maximum. I'm going to get a minimum magnitude of force if they are opposing each other. I got 24 newtons there, I have 18 newtons there. And so now I have 24 minus 18, which is 6 newtons. That's the minimum. There's the maximum, and that's the answer to part A. So problem number 11 is really about weight versus mass. And the formula, weight is equal to mass times acceleration due to gravity. So I weigh a book on Earth and it gets a weight of 21 newtons. So weight of book on Earth is 21 newtons. The acceleration due to gravity on Earth is approximately 9.8 meters per second squared. Now some people will round it up to 10. Some people will round that up to 10, and some people would put 9.81, which is a world average to 3 significant figures. But I tend to use 9.8, although occasionally I'll just come up with a magical planet where it's actually equal to 10. And so the mass of the book, well, if that's my formula there, what times 9.8. So basically the math problem is 21 is equal to mass times 9.8. That's the math problem. Divide by 9.8. And the mass ends up being 2.143. Now units, this 21 was in newtons, and that's in meters per second squared. And so we could have units of, well, let's work that out over here. So if 21 newtons is equal to mass times 9.8 meters per second squared, if I divide by 9.8 meters per second squared, I end up with mass on the right side. Those cancel out. On the left side, I had the 2.143, and then my units are newtons over meters per second squared. Now that's an awkward set of units there. Now we have a couple of shortcuts here. One, if we knew that newtons is an SI unit and meters per second squared is SI, in other words, international standard, which means my mass, my final answer, has to be international standard, and so that has to be a kilogram. So if you remember that a newton is a kilogram meter per second squared, then if I divide by meters per second squared, divide both sides by meters per second squared, meters per second squared cancel out on the left, and I see that newton over meters per second squared is indeed a kilogram. So 2.143 kilograms. That's the book. I weigh a table on the moon and I get 21 newtons. And again, we're going through the same process here, except the difference is I still have 21 is equal to mass times acceleration due to gravity on the moon. This 9.8 is not a constant, and so on the moon it is 1.625, somewhere around that range. Depends upon the source, might give you a slightly different answer. That's meters per second squared. And so my mass is 21 divided by 1.625, which is 12.923 kilograms. Table is brought to Earth. What is its mass now? Mass is not location dependent, and so the mass should be the exact same thing as the table was on the moon. So those two answers are the same. When the table is on Earth, what is its weight? What is its weight? Well, we're plugging in a W equals mg. I know the mass now, 12.923 kilograms, 9.8 meters per second squared, because now I have a different acceleration due to gravity. And this ends up being 126.65 newtons. And the book's weight on the moon, well, we're doing the exact same formula here, W equals mg, except this time we're using that value for g. I know the mass, and so the book's weight will be W equals mg, and that will be the mass, which is 2.143 times 1.625, and I got 3.48 newtons. So this is emphasizing that the mass does not change, and the weight does, depending upon where you are. So I bounce on a work analog scale, causing the dial to move. So if we think about, if I have a scale here, and I have a person on it. So recall on the video or in class that if we look at the forces acting on the person, we have normal force up and we have weight down. That normal force up is met by a reaction of that same normal force acting down, same magnitude of normal force. So what the scale is actually measuring is that normal force. So we have normal force up, we have weight down. And so we'll get more magnitude of, we'll have the scale read more than the magnitude of my gravitational pull on me, and the gravitational pull on me is my weight when the normal force is greater than the weight. Well, when you are bouncing, remember as you bounce, you slow down, you stop, and then you come back up. In order to stop, there must be a net force acting upwards on you. And so at the bottom of your motion, because that's when you get to that maximum in this direction and you're about to come back, there has to be a net force on you to make you go back. Not the top of a motion, because that's the exact opposite of the bottom. when I move down, slowing down, so if I'm moving in this direction and I'm slowing down, my acceleration must be up. Some of this is a chapter 3 concept, but if I'm moving down if I'm moving down and slowing down, my acceleration is upwards, and that has to be the direction of the net force. In other words, the normal force is bigger than the weight. Move down, speeding up, that means my acceleration is down, my weight has to be bigger than my normal force. When I moved up, slowing down, so now I'm going in this direction, so my acceleration is down, so the weight is dominant. That's what causes me to stop in order to come down. Move up, speeding up. Acceleration, velocity in the same direction, and accelerations in the same direction as the net force. And then move down and moved up. These are just way too generic. So B, D, and G are the answers. 13. 35 kilogram boy on a 6 kilogram sled. So let's take a look at that. I'm going to do a little force diagram here. I have boy and sled and ground. So if I look at the boy here, I look at the sled, and I look at the ground. I'm given in the problem the sled is being pulled horizontally by a rope. So the rope's pulling horizontally to the right, so there's a tension there because there's a rope pulling. Friction is to the left, and so there's got to be a friction acting this way. Now this is an example, sort of an example of other. There's something over here for which there is a force pulling back, the tension pulling back this way, but that we don't know what that is, and so I'm only going to do one of these. And the friction between the sled and the ground is 42 newtons, and that is the same as the tension in the rope. I have the sleds being pulled horizontally, and which keeps the sled moving horizontally. So the sled is going to be moving horizontally. That means no up and down. So I'm in equilibrium vertically, and because of this, I'm in equilibrium horizontally. This is an equilibrium problem. Now let's get the other forces involved here. I have a weight of the boy. Weight of the boy. I have weight of the sled. Weight of the sled. I have normal force acting up on the boy and a normal force acting down on the sled. And then a normal force acting up on the sled from the ground and a normal force down on the ground. If the sled leaves any track marks in the snow, it's that force right there which is causing it. That combination of that and the friction. So now, magnitude of the gravitational force acting on the boy. In other words, that is asking for the weight. We have a formula, mg. I give you his mass, which is 35 kilograms, and then we assume it takes place on Earth. I guess if you solved it with a different planet, I could not take off for that, as long as you were consistent. And I ended up with 343 newtons. The part B, what is the magnitude of the gravitational force acting on the sled? I'm asking for this. This is equal to mg. The mass is 6 kilograms times 9.8. Again, same planet as before. And this is 58.8 newtons. The magnitude of the normal force acting on the sled from the boy. So magnitude of the normal force acting on the sled from the boy, that's this force right here. In other words, that right there. Since the boy is in equilibrium, that has to be equal to the weight. It's not always the case, but it is in this case. And so that's 343 newtons. The magnitude of the normal force acting on the sled from the ground, that is this force right here. In order to figure out, I need to figure out this one. So if I look at the sled, I have its weight acting down, 58.8 newtons. I have the boy pushing down on the sled with 343 newtons. And then Y sub S is what's holding it up or keeping it from falling through the ground. And so that has to be the sum of these two. The forces up equal to forces down. And so this would be 401.8 newtons. And the magnitude of the total force acting on the sled, well, if the sled's moving in equilibrium, the total force has to be 0. Doesn't matter the rest of the stuff, but, well, we actually built that into the assumption of how we solved some of this, but it's 0 newtons. And the magnitude of the friction force acting on the boy from the sled, if we assume that the boy is sitting on the sled, staying with it, then the boy is also in equilibrium. It would also be 0 newtons. So equilibrium, oh, sorry, write it right there. Equilibrium, don't forget, the total force is equal to 0. Acceleration is equal to 0. Change in velocity is equal to 0. If one of these is true, the other two are automatically true. All right, woman gets into push-up position and starts her daily exercise. She pushes on the floor and moves upwards. While moving upwards, she speeds up, then slows down. While she is moving upwards and slowing down, so she's moving in this direction and slowing down. So acceleration and therefore net force are down. And again, if we think about the forces, we have a normal force acting up, we have a weight acting down. Since the net force is downwards, the weight has to be bigger than the normal force. However, oh, sorry. I'm jumping ahead there. She pushes on the floor with 240 pounds of force during this moment. The floor pushes on her, and this was a slightly different problem. If we look at her, we have normal force acting up, weight acting down, weight acting up, normal force acting down. So the question is asking for a comparison between this force right here and that force right there. And they are equal in magnitude, opposite in direction, so it is the same. This time we're not comparing the action and reaction force. We have, he speeds up, slows down while he's moving up and slowing down, so that's this situation. So he's moving up, slowing down, so acceleration is the opposite, or the net force is downwards. We still have weight and normal force acting on him. And so the weight is bigger than the normal force, and I'm asked to compare the force with which the Earth pulls on him, that is this force right here, is, well, he's pushing on the floor with 240 pounds of force, so that's 240. Weight has to be bigger than that. All right, so 16 through 19, again, force diagram. 16 through 19, a force diagram right here, so let's sort of sketch that out. So whenever you're doing a force diagram, you draw the objects separately. So I have mass 2 here, mass 1, and ground. And now do my checklist. So weight, of course, we have weight 2 acting down there and then up on the ground. We have weight 1 acting down on mass 1 and weight 1 from the ground. Done. Normal force, I have normal force y1, y1, y2, y2. Other, we have an other in this case because the problem states that there is a problem, F sub p, which is equal to 50 newtons, and that value is irrelevant as far as this problem goes, the way I've worded this problem. And then friction. So if this is going to be moving that direction, so the friction opposes that, and then acting that way on the ground. And then there's friction between these two. I know that mass 2 is going to be moving to the right. Mass 2 slips a little on top of M1, but for the duration of the problem, M2 also moves to the right. So it's moving to the right. So there has to be something that's going to get it to move. If it starts at rest, something will have to start it moving. If it was already moving, then not necessarily. But there is a little bit of slipping. And which way is it going to slip? It's going to slip backwards. And so friction opposes that slipping. So F2, oops, sorry, F1, F1. And it looks like I got my subscripts a little backwards there, but let's go with it for now. So the direction of the friction acting on M1 from the ground. So the direction of the friction that's acting on M1 from the ground, that is this right here. So that is acting to the left. The direction of the friction acting on M2 from the ground, well, the friction acting on M2 is coming from mass 1. Friction requires contact, and the ground and M2 are not touching, and therefore that does not exist. The direction of the friction acting on M2 from M1, well, that's the friction acting on M2 from M1, and that's acting to the right. And the force which is moving M2 to the right, well, that's the friction from M1. It's directly related to this one. Problem 20. What matters is the relative motion, even though M1 ultimately is moving down, but it's moving up relative to M2, which means this one is slipping faster than this one is, which means M2 is dragging down on M1. So if I have M1 here and M2 here, M2 is moving down faster, and therefore it's dragging down here. The friction from M1 on M2 is trying to oppose that, and so the friction on M2 is up, and the friction on M1 is down. There are a couple of ways of looking at this, but I'm going to do it the vector addition way. So I know that this is an equilibrium problem, and the reason I know that is straight line at a constant speed. My velocity is changing, so the change in velocity is 0. Therefore, it's equilibrium, which means that the total force is 0. The total force is 0, I end up back where I started. So I just start with one of them. I go down, just starting with that one, then I go off to the left, and then I'm going to make that longer there. So weight coming down, I have this F sub k acting this way. I go up with y. Since Ft is acting up and to the right, it has to go like this. There's my normal force, and there's Ft. And so just looking at the length of the arrows, I can see that this is longer than that is. If you think about a triangle there, the base is Fk, but the hypotenuse is Ft. Hypotenuse is the longest. So that brings it down to here. Also looking at this, I know that the weight has to be greater than the normal force, just looking at the picture there. So we have this one. Another way of looking at it is I can break any force up into its components. This piece right here must equal this piece in order for it to be in equilibrium. Therefore, this length is Fk. So my hypotenuse here, similar to what I was talking about before, my hypotenuse has to be bigger than this length of the triangle, and therefore Ft is bigger than Fk. And then in terms of upward forces, I have weight acting down, but I have normal force and this piece right here both acting up. If some positive number plus another positive number must add up to W, and so this the normal force must be less than the weight, because I have these two forces acting up, one acting down. And then the big force diagram. Put my F down here. So I still find weight the easiest, so I'm going to put in weight. So I have weight of person, weight of person. Forces come in pairs. The only time I would not draw a pair is if other was involved, but there's no other in this particular problem. I have weight of the table, weight of the table, weight of the tablecloth, weight of the tablecloth, weight of the vase, weight of the vase. And let's not forget the ceiling, weight of the ceiling, weight of the ceiling. So weight is done. Now I could add in weight of the rope. I do state that it's a frictionless, massless, so I do state frictionless, massless, stretchless rope. That is ideal. But the key thing there, it's massless, and so there is no weight. And let's do tension. Tension is relatively easy once I have the rope. I know tension has to be acting down here, and tension has to be acting up here. If tension's acting down, it's being pulled down by the hands, so it must be pulling up on the hands. So I have tension there. Those tensions are, this is a pair. Forces come in pairs. That is the pair right there. And then here and here, that is a pair right there. And so if you're going to do subscripts, these two will have the same subscript. These two will have a different than the previous one, but these two will share the same subscript. I have one rope. I've taken care of both ends. Done. Normal force. Well, normal is between any two objects that touch. So I have y sub p and y sub p. Rope and ceiling touch. So rope is being pulled up here. Y sub, we'll call it R1. Y sub R1. Down here, I have y sub R2. y sub r2. Now, some students will throw in the relationship between the pulley and the ground, and that is not necessary, because the way I've drawn this is I've made this pulley part of the ground, so this is all one object. And that's one of the reasons why I break it apart for you, so you don't have to guess about what the different parts are. And I have rope and, ceiling and this pulley as combined. All right, so now hands and rope are touching. I don't know how that he has it, whether he has it wrapped around his hands or he's just pulling on it. I don't know what the force is between the hands and the rope specifically. I don't know if it's a normal force or friction, so we're just lumping that into tension. Once I have tension labeled, I don't need to throw in any more specifics than that. Table and ground touch, so I have y sub t and y sub t. I only have to do one normal force of acting up on the table, even though there's 2 legs. Or maybe there's 4 legs, or maybe there's 8 legs. We don't know, just all the normal forces combined. I'm just lumping into this. Tablecloth and table are touching, so y is tablecloth, y tablecloth, and then vase and tablecloth are touching, y vase, and y vase. And now friction. The tablecloth is being pulled off to the right. The table wants to oppose that, so the table is going to add some friction, called F sub Tc, and so F sub Tc going this way. The vase also, if anything, is going to slip back, and so the tablecloth wants to oppose that, so the tablecloth is F sub V and F sub V. And since the table is being pulled to the right slightly, not in reality, not a whole lot, but it's being pulled to the right, if the floor were frictionless, that table would be dragged along with the tablecloth, and so the force is going to oppose that, so force on table, friction force on table, friction force F sub T on the ground. And him. So notice that these two are acting vertically. This force right here is has a slight component to the left, and so therefore on a frictionless floor he would actually be pulled to the left, and the ground doesn't like that, so F sub P, F sub P. And that should be it. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to compare to what I had before. I had 10 on the ground, so that's right. 1, 2, 3, 4, 5 on the table. That matches what I did before. 1, 2, 3, 4 on the person. Yep. 1, 2, 3, 4 on the rope. 1, 2, 3, 4, 5, 6 on the tablecloth. And 1, 2, 3 on the vase. And 2 on the ceiling. Yep. So that's 34 forces total. If you're looking at something that I've graded, if I do a squiggle, that means wrong direction. A circle means wrong label. A circle with a squiggle means that wrong direction and wrong label. X just means that force just doesn't belong there. Everything's copacetic. And those are the 4 major markings that I make on a paper. Out of 34, this is worth 1 point. These are worth a half point. This is worth 0 points, and this is minus 1/2. And that is Master Set 2.